Okay, so what we have here is a Cauchy-Euler differential equation, which remember has the assumption that the solution will carry the form y equals t to the mu power. I like to use Greek letters, what can I say? So in order to make this assumption work, we take derivatives and substitute and see if we can make it into an equation exclusively in the letter mu. So just using the power rule, we have y prime is mu t to the mu minus 1, and y double prime is mu times mu minus 1 times t minus 2. So basically, we're substituting for y double prime, y prime, and y. So you have 2t squared times mu minus 1 times t to the mu minus 2 minus t times t to the mu minus 1 plus, and y is t to the mu, and we want that to be equal to 0. So the immediate thing I see is that some powers of t can be collected here, and wouldn't you know, they all turn out to be t to the mu. So we have 2 t to the mu times mu minus 1 minus mu times t to the mu plus t to the mu equals 0. Now there's a t to the mu term in each term, so I'm going to factor that out. And this is the big deal right here. So we have this. And now you notice that the inside expression only has mu's in it. So that's going to be the key to figuring out our values of mu. So remember, for t to the mu to be 0, t has to specifically be equal to 0. And we're trying to solve a differential equation for a function of t, that's not going to work. So we can basically ignore that. In fact, when we're dealing with Cauchy-Euler solutions, we can safely say that t is not equal to 0. So that's a situation for later. But since we're assuming that y is t to a power, if the power is negative, we can't substitute t equals 0 anyway. So we just make that assumption. So solving the inside piece equals to 0. So now we have, now we have 2 mu squared minus 2 mu minus mu plus 1 equals 0, which means 2 mu squared minus 3 mu plus 1 equals 0. And that actually factors. So we have 2 mu minus 1 equals 0. And by eyeballing this, I see that mu is either 1/2 or 1. So great. That says that if t to the mu is a solution to this differential equation, then mu would have to be 1/2 or 1. Great. Second order differential equation, 2 linearly independent solutions. I think we've figured it out. So that means that y is equal to c1 times t to the half. We could write it as square root of t, but we're not going to because we're going to be using this further with some calculus, plus c2 times t to the first, which is just t. So there's our general solution. Beautiful. So now what we're going to do is substitute use our initial conditions to find c1 and c2. So we know that y of 1 is 2, which means when I plug in 1 for t, I get 2 for y. So that says 2 is equal to c1 times 1 to the half plus c2 times 1, which leads to the equation c1 plus c2 equals 2. Okay, so now we need another equation to be able to figure definitively what c1 and c2 are. So we're told that y prime at 1 was equal to, I thought it was 4. Oh, but we need y prime first. So y prime is 1/2 times c1 t to the negative half plus c2. So y prime at 1 is 4, and that's also equal to 1/2 times c1 times 1 to any power is 1 plus c2. And there's our other equation. So I'm going to write that as 1/2 c1 plus c2 equals 4. So there's our two equations, and we could either use substitution, elimination, use a matrix, and do reducible echelon form, whatever floats your boat. I'm just going to subtract one equation from the other, so I'm going to subtract this from this. So I have c1 minus 1/2 c1, so that's going to be 1/2 c1 C2 minus C2 is 0. That's why I'm subtracting. And 2 minus 4 is negative 2. So that means C1 is equal to negative 4. And since we're told that C1 plus C2 is 2, if C1 is negative 4, C2 is 6. So then the final solution is y equals negative 4 t to the half plus 6t. And that solution not only satisfies the differential equation, but also the initial conditions. Thanks for watching.